Hey everyone, especially all you Class 10 students gearing up for your exams. You've landed in exactly the right place. Today we're going to totally demystify the magnetic effects of electric current. Think of this explainer brought to you by the amazing team at A1 Institute as your secret weapon to ace this topic. So let's jump right in.
You ever look at an electric motor and just wonder, how does it actually work? Well, it's not magic. It's this incredible, invisible dance of forces. See, when you have an electric current, it actually creates its own magnetic field. Now, what happens when you put that wire inside another magnetic field? They interact. They create a real, actual push or a pull. And that force, well, that's what makes everything move.
Okay, so we've established there's a force. That's the easy part. But which way is it going to push? Up, down, left, right? For your exams, and honestly, for anything in the real world, getting the direction right is absolutely everything. So how on earth do we figure that out perfectly every single time?
Well, lucky for us, there's a trick. It's kind of like a secret handshake for physicists, and it's your key to unlocking this whole puzzle. It's called Fleming's left-hand rule, and once you get it, you'll never get the direction wrong again. Let me show you.
Okay, so the official definition sounds a little textbooky, right? But all it's saying is this. Take your left hand. Now stretch out your thumb, your pointer finger, and your middle finger so they're all pointing in different directions, kind of like a 3D axis. That's it. This simple hand shape holds the secret. And seeing it like this is where it really clicks. Trust me, remembering this picture is going to be way easier in an exam than trying to recall a boring paragraph from a book. Each finger has a very specific job to do in our little secret handshake.
And here is the ultimate memory trick. You ready? Just think FBI. No, not that FBI. Your forefinger is for the magnetic field. Your center finger is for the current, and that leaves your thumb, which shows you the direction of the thrust or the force. Some people like to remember it as father, mother, child for force, magnetic field, current. Whatever works for you, just lock it in.
So theory is cool and all, but let's be real. Applying it is what's going to get you the marks. So let's put our new secret handshake to the test with a classic exam-style problem.
All right, check this out. We've got an electron, and it's moving upwards, from the bottom to the top. It's passing through a magnetic field that's pointing to the right. Our mission, should we choose to accept it, is to figure out which way the force is going to push that electron. Time to get our hands ready.
But hang on, stop. This is so important. This is the little detail that trips so many people up. By convention, just a rule we all agree on in physics, the direction of the current is always the opposite of the direction that electrons are flowing. So if our electron is moving up, which way is the current flowing? You got it, it's flowing downwards. Don't forget that.
Okay, let's do this together. Get your left hand out. Point your forefinger, that's the field, to the right. Good. Now point your center finger, the current, downwards. Now just look at your thumb. Where's it pointing? Straight at the screen, right? Or, as we'd say in an exam, into the page. And that's it. That's our answer. See? Not so bad.
All right, let's bring all this theory back home. Literally. Because these exact same principles are at work right now inside the walls of your house, powering your whole life.
So behind your walls, you've basically got this team of 3 wires doing all the work. You've got the live wire, usually red, carrying the high potential, about 220 volts. Then you've got the neutral wire, which is black. It's at 0 volts, and its job is to complete the circuit. And then there's the green earth wire. Think of that one as your silent bodyguard, a super important safety feature.
And speaking of bodyguards, let's talk about maybe the single most important safety device in your entire house, the fuse. It's this tiny little guardian that stands watch, protecting all your expensive gadgets and appliances from 2 very specific dangers.
So what are these dangers? Overloading and short-circuiting. Overloading is what happens when you plug way too many things into one outlet. You know, the TV, the game console, the phone charger. The current starts to slowly creep up. A short circuit is way more dramatic. That's when the live and neutral wires actually touch. When that happens, you get a massive, instant surge of current. Both of these can cause fires, but that's where our little hero, the fuse, steps in.
Let's see this little guardian in action with a quick problem. Say you have a powerful 2-kilowatt electric oven. You plug it into a 220-volt line, and that circuit is protected by a 5-amp fuse. So the big question is, what's going to happen when you switch that oven on?
To figure this out, we just need one simple but super powerful formula.
You absolutely have to know this for your exams. Power equals potential difference times current, or P equals V times I.
So let's break down what we know. The problem tells us the power, P, is 2 kilowatts. That's just 2,000 watts. The voltage, V, is 220 volts. The thing we need to find is the current, I.
So if we just rearrange our formula a little bit, we get that current equals power divided by voltage. So we just plug in our numbers, 2,000 divided by 220. And that gives us about 9.09 amperes. This is how much current that big oven needs to run.
Now for the moment of truth. The oven wants to draw 9.09 amps of current. But look, the fuse is only rated for 5 amps. So what happens? The fuse does its job perfectly. The instant that current goes above 5 amps, the tiny wire inside the fuse will melt, it will break the entire circuit, and it will stop that high current from damaging the oven or, even worse, starting a fire. Pretty cool, huh? Woo! We have covered a ton of ground. So, before we wrap up, let's do a super quick, rapid-fire recap of the key things you absolutely need to remember for your exam.
Okay, deep breath. Remember, a wire with current in a magnetic field will feel the force. To find the direction, use your secret weapon, Fleming's left-hand rule. At home, you've got 3 wires, live, neutral, and earth, and the standard voltage coming out of your walls is 220 volts. Got it? Good.
And when it comes to safety, the fuse is your #1 hero. It protects you from 2 things: overloading, which is just plugging in too much stuff, and short-circuiting, which is when those live and neutral wires touch.
I really hope this breakdown makes you feel way more confident for your exams. If you want more detailed notes, expert guidance, or you're interested in admissions, you should definitely get in touch with our friends at A1 Institute. And hey, if this was helpful, do us a favor. Like, share, and subscribe for more explainers like this one. All the contact info you need is right there in the description below.
And I'll leave you with one final little puzzle to think about. We know the fuse is there to protect the appliance. But what about that green earth wire, our silent bodyguard? How exactly does it protect you from getting a nasty electric shock? Have a think about that one. Thanks so much for watching.